So we're going to do exercise 11 from Atiyah and Macdonald's Introduction to Commutative Algebra. And this exercise is all about boolean rings. So let's first talk about what a boolean ring is. Pretty simple. It means that every element is idempotent. So x squared is equal to x for all elements in this ring. Then we're going to show three basic properties, namely, 1, that 2x is equal to 0. Second property is that every prime ideal is maximal, and B mod P has two elements for any prime ideal. And the third property is that every finitely generated ideal is principal. So before we prove these three properties, let's go over some basic facts. You should know these. Namely, if I is an ideal, then extending it by an element not in I, if that gives the entire ring, then I is maximal. Second fact is if you have two elements x and y, and they differ by an element in I, then their cosets with respect to I are going to be the same. And the third and last fact is if x is idempotent, it means that x multiplied by 1 minus x is equal to 0. It's pretty easy to see if you multiply it out. So let's do the first property, which is that we have to prove 2x is equal to 0. Well, it's pretty easy to do, but we have to be mindful of one thing, and that is that 2 is not a ring element per se. We're considering 2 to be the action of the integers onto this boolean ring, and so by 2x we actually mean x plus x for every element in the boolean ring. And showing this is pretty easy then, because we can just square it. We get all these elements, and then, well, these are all squares. We know squares don't really matter in a boolean ring, so we just remove them all, and then we can just see that, okay, x plus x is equal to x plus x plus x plus x. And so we can take away two x's, and automatically follows that x plus x is the 0 element. Okay, good. Let's show the second property, which is the hardest in my opinion. We have to show that every prime ideal is maximal. Okay, so to show this, we're going to fix a prime ideal P, and then we have that for every element in B, either it is contained within this ideal, or 1 minus x is contained within this prime ideal. And this follows directly from the fact number 3, namely x times 1 minus x is equal to 0, and 0 is contained within any ideal, so it's also contained within the prime ideal. What this means is that 1 of x and 1 minus x has to be in the prime ideal. But obviously they can't both be in a prime ideal, since by closure of abelian groups that would generate 1, and you cannot have 1 inside an ideal. So we know that for all elements in B, either x is in this prime element, or 1 minus x is inside this prime ideal. Okay, but what this implies is that if we have an element that's not inside this prime ideal, then 1 minus that element is inside this prime ideal. Which means that if we extend this prime ideal by any element not in it, we are going to get the entire ring, since 1 minus y plus y is equal to 1. And by fact 1, that means that it is maximal. Let's show the second part. It's pretty easy to see. If we have this morphism taking B to B mod P, we can just kind of look where every element ends up. So if you have an element inside P, it's obviously going to be mapped to 0. And if your element is not inside P, then 1 minus x is inside P. And it follows directly from fact number 2, that then it gets mapped to the coset 1 plus P. And so you can see that B mod P is isomorphic to Z mod 2Z. And so it has two elements. Last property, every finitely generated ideal is principal. Pretty easy to show too. We have to do it by induction. So base case is going to be one generator, which by definition is already principal. And our inductive step is going to be, okay, if we have an ideal with m generators, that is principal, then extending it by a generator also is going to give a principal ideal. And so we can assume we have such an ideal with m generators that is principal, which just means that we have an element G1 that generates this entire ideal. Then we're going to pick some element to extend it by, and then we're going to consider all the elements that are inside this extended ideal. So they're going to consist of bilinear combinations of G1 and G2. And the next step I'm going to leave up to you, and that is to verify that the element G1 plus G2 plus G1 times G2 is going to generate every such element here, and every such element there is also contained within there. And once you've verified that, we can just say, okay, by induction, every finite generated ideal is principal.